Hello, welcome again. We are covering the topic axial flow compressor for civil services mains, IFS and GATE aerospace exam. And next subtopic in the main topic of axial flow compressor is work done factor. We have derived the expression for work done and stagnation temperature rise in the previous video. This was your work done and this was your stagnation temperature rise. But actually the experiment shows that this stagnation temperature rise is more as it is given by the equation, assuming Ca is constant. And experiment shows that actual stagnation temperature is less than this value. So there is some losses or some drawbacks in this that we will discuss, and to account for these drawbacks or losses we will introduce a work done factor. Okay. So as we have assumed that Ca is constant, but actually the Ca is not constant. So this is the line showing Ca constant. So this is your first stage and this is your blade height, and this is your blade root, and this is your blade tip. Here we can see that the Ca at the tip and root is less than mean, and at the center it is more than mean. This is your first stage, and these variations become more prominent as the number of stages or as we move ahead. So in the fourth stage, this is the velocity profile, and after that this velocity profile becomes stable, so it will remain PP at the center and remain depressed at the edges. Okay. So these variation reduces the work done or stagnation temperature rise. So this was the actual stagnation temperature rise, where we considered Ca as constant, but actually when we take the variation of Ca, this stagnation temperature rise as well as work done decreases. Okay. How it is decreases? So this was the expression for work done that we have derived, that is W is equal to mu Ca tangent beta 1 minus W beta 2. Okay. From velocity triangles we have, from first inlet velocity triangle, U is equal to Ca tangent beta 1 plus Ca tangent beta 1, or U by Ca is equal to tangent alpha 1 plus tangent beta 1, or tangent beta 1 is equal to U by Ca minus tangent alpha 1. Okay. So here if we put this value of tangent beta 1 here in this equation number 2, then we get this expression mu large bracket U minus Ca small bracket tangent alpha 1 plus tangent beta 2 bracket close and large bracket close. Just put in the value of tangent beta 1, so we get this equation. So here we have got the expression in terms of alpha 1 and in terms of beta 2. So alpha 1 is, if we see the velocity diagram, this is your alpha 1. So this is inlet angle of rotor, or we can say outlet angle of stator. Okay. Or it is outlet blade angle of stator, because stator is stationary, so we will take the absolute velocity. And beta 1 is your, beta 2 is your outlet angle of rotor blade, as rotor is not stationary, so we will take relative velocity angle. So that is your constant quantity. Beta 2 is constant quantity because this is outlet angle of rotor, and alpha 1 is also stationary quantity because this is outlet angle of stator or inlet angle of rotor. So these two are having fixed value because these are the outlet angle of two blades, that is rotor and stator. Okay. So now these are constant quantities, alpha 1 and beta 2. U is also given constant. So W will vary only with Ca. So as Ca increases, work done reduces. Okay. So and we have seen that CA is peaky at the center and less at the corners. So net effect of this variation of CA is to reduce the work done. So work done is reducing with CA. So to compensate for this, we will take mean CA and introduce a work done factor, that is your lambda. Okay, or CPT not as your work done, or we can say work done will be your lambda u CA tangent beta 1 minus tangent beta 2. Actually the expression was mu CA tangent beta 1 minus tangent beta 2. So now we introduce a work done factor, that is lambda, to get actual work done. So which is called work done factor, and it is less than 1. Okay. As the number of stages increases, this work done factor decreases. So I will read out this so that you can note down. The first point is, experiment revealed that the stage temperature rise was always less than would be given by equation T03 minus T01 is equal to T02 minus T01 is equal to UCA by Cp bracket tangent beta 1 minus tangent beta 2. So this is equation number 1. The explanation of this is based on the fact that the radial distribution of axial velocity is not constant across the annulus, but becomes increasingly peaky as the flow proceeds, settling down to fixed profile to about 4th stage. This is your 4th stage. This is shown in figure, which shows the typical velocity profile in the first and 4th stage. Now the work done per second is W is equal to mu CA bracket tangent beta 1 minus tangent beta 2 bracket close. From velocity angle, U by CA is equal to tangent alpha 1 plus tangent beta 1, and U by CA minus tangent alpha 1 is equal to tangent beta 1. Okay. So here, putting the value of tangent beta 1, W will be mu CA bracket U by CA minus tangent alpha 1 minus tangent beta 2 bracket close, or mu bracket large bracket U minus CA bracket tangent alpha 1 plus tangent beta 2 bracket close, large bracket close. Okay. The outlet angles of stator and rotor blades determine the value of alpha 1 and beta 2, okay, which can therefore be regarded as fixed, unlike alpha 2 and alpha 2, which vary with C. So these are not dependent on C. Equation 4 is your this equation. This equation shows that an increase in CA will result in decrease in W if it is assumed that the compressor has been designed for constant radial distribution of axial velocity as shown by dotted line. The effect of an increase in CA in the central region of the annulus will be to reduce the work pressure loading in that area. Here or here. The reduction in CA at the root and tip might be expected to compensate for the effect by increasing the work capacity of the blading flow to another point. So here work capacity decreases and here increases. Unfortunately, the influence of both the boundary layer on the annulus wall and the blade tip middle has an adverse effect on the compensation. Okay, and the net result is to decrease the total work capacity. The reduction in work capacity can be countered by the use of work done factor lambda, which is a number less than unity. The actual stage temperature rise is given by 4. Okay. So this was your actual station temperature rise, and work done will be a Cp into m into this temperature.